Since 1900, over 10,000 people have lost their lives in tornadoes, and they have caused billions of dollars in damage. Why and where one will form next are important questions, for as our cities grow, so do the chances of a tornado hitting a populated area. A source of mystery and misunderstanding for centuries, it is nature's most violent windstorm. The unique geography of North America makes them more common here than anywhere else in the world. A small area of low pressure, it is usually less than half a mile wide, yet capable of enormous damage. Answers are hard to come by, for this marvel of nature lasts only several minutes and is too dangerous to approach. We must devise methods to study it at a distance. Information from past tornadoes is a place to start, for among other things, it can give us a picture of what areas of the country are most likely to be hit. If our unit area is a large square, 50 miles on a side, then on a long-term average, some part of an area that size, in the yellow, would experience one tornado about every 8 years. In the orange, the frequency would be about one every 2 years. In the red, one every year. And in the purple, more than 2 tornadoes each year. It has been found that the area of highest frequency changes considerably each month. Most tornadoes in the spring occur in the southern states. And as spring progresses, this area shifts to the north and west as warm air penetrates further and further northward, and eventually shifts back to the south during the fall and winter months. To forecast the possibility that a certain area of the country might be hit on a particular day, we need more information than just a yearly average. We need to try to understand the very complex weather conditions that might cause a tornado to form, and then be on the lookout for them. The flow of air in the high-altitude jet streams is important, as are the movements of air masses nearer the surface, and the possible formation of a squall line out ahead of a cold front. For instance, on the morning of June 8, 1966, some of these ingredients were obvious. The isobars and fronts on the surface map showed a large storm in Oklahoma moving northeastward. A strong jet stream was flowing out of the southwest high over Kansas. At the surface, a squall line developed in the warm, moist air out ahead of the cold front, and the Weather Service issued a tornado watch for most of eastern Kansas. The actual tornado warnings came at 7 p.m. when a funnel was sighted southwest of Topeka, Kansas, moving northeastward. The path was only a little longer than average, 22 miles, but right through the heart of the city, destroying 200 homes. The death toll, which was 17, could have been much higher without the many warnings that were issued and followed. History has shown that these ingredients can combine well outside of the area of usual tornado activity. In June 1953, a cold front and squall line spawned a series of tornadoes in the Great Lakes area, hitting Erie and Cleveland, Ohio, killing 116 at Flint, Michigan, as 200 homes were destroyed on a single street. Weakening at night, the storm spared New York and Pennsylvania. But in the heat of the next afternoon, the squall line reformed and spawned a tornado over unsuspecting Worcester County, Massachusetts. 90 people died and 1,300 were injured. Debris such as roofing material and clothes were drawn up into the thundercloud, carried eastward for 50 miles, and dropped from the clouds onto the Boston area. There was no squall line over Dallas, Texas in April of 1957. Just warm, moist air being drawn in from the Gulf of Mexico at the surface. A low-altitude jet stream also from the south, and a high-altitude jet from the west. The product was 20 tornadoes. And this one in Dallas became one of the most well-photographed and studied tornadoes in history as it tore a 400-foot wide path across the west side of the city. The causes of each tornado are enormously complex, and much is not understood. But the main ingredients can be identified and forecasted better than ever before. Photography has been a valuable tool in tornado studies. Most photographs have been taken by non-scientists, and usually on chance, for it isn't yet possible to predict the exact location that a tornado will strike. These have given a rather complete picture of the visible life history of a tornado. From the first rotating clouds, to the slow condensation of water to make the funnel visible, although a visible funnel isn't necessary to have a destructive tornado. And to the final stages as the funnel becomes thinner, elongated, and finally leaves the ground for the last time. The speeded-up photographs of time-lapse photography are now an important tool in many weather studies. These are made by taking single photographs every few seconds or even every few minutes, and then projecting them at the normal rate of 24 each second. This gives a view of a thunderstorm or squall line that can't be obtained in any other way. In June of 1966, this giant rotating thundercloud was being photographed in time-lapse over South Dakota when the camera captured the entire life cycle of a tornado beneath the cloud on only a few seconds of film. The motion of the storm can now be slowed down and studied at any particular instant. By slowing down the motion of a tornado, we can see in detail the rotation of the funnel and the explosion of buildings into the extreme low pressure. The circulation can be studied by following and measuring the movement of single pieces of debris. In this way, the winds of the Dallas tornado were estimated to be at least 170 miles an hour. Engineers studying structural damage and the overturning of 50-ton railroad cars in the same storm estimated winds of over 200 miles per hour. Studies of bent high-voltage towers in the Worcester tornado gave estimates even as high as 330 miles an hour. But tornado research can take place well away from an actual tornado. There are many tornado-like phenomena that are more approachable, at least to some degree. The great amount of heat and moisture in the clouds above active volcanoes, like Surtsey off the coast of Iceland, can produce tornado-like whirlwinds. They would make an interesting study and are confined to a small area. But working near an active volcano is obviously dangerous. There is a large whirlwind, however, that can be studied with less danger. The waterspout. Not as large or powerful or unpredictable as a tornado, Its entire life cycle can be studied at a reasonable distance from an airplane. Often considered to be no more than a tornado over water, the waterspout is in many ways quite different. It can form from clouds that are no more than a few thousand feet thick, and it usually has a smooth, cylinder-shaped funnel. The winds whirling around the calm eye are seldom more than 150 miles per hour, and are probably created by a very different mechanism than that which creates tornadic winds under thunderstorms. But despite these differences, it is a violent whirlwind, and the closest thing to an actual tornado that can be easily studied. The circulation in and around the funnel is of prime interest, for if the circulation is understood, maybe it can be weakened when a populated area is in danger. It can be studied by dragging a temperature and pressure recorder behind an airplane and swinging it right through the funnel, and by dropping flares on water and tracing the path of the smoke as it is drawn into the water spout. In its early stages, a circulation is present long before a visible funnel appears, and the only visible sign is a dark spot on the ocean surface. Could something like this be true of tornadoes? And could it be detected? Other studies with time-lapse photography have shown that waterspouts decay near a rain shower, possibly due to the cooler air near the shower. The waterspout looks as if it will be an important tool in future tornado research. There is an even more approachable whirlwind that can be studied, the much smaller dust devil. These form over hot, dry country and are very frequent in some desert areas. Winds may spiral at over 100 miles an hour, but 30 is much more common. They've been quite useful in studying the movement of air around and inside of a natural vortex. Studies have shown that the air in the very center is moving downward and rising rapidly just outside of the core. This is suspected to be the case with at least some tornadoes and waterspouts. Experiments have been carried out in destroying and creating dust devils artificially, always with an eye on whether any new knowledge can be applied to their big brother. There is yet another possibility: the controllable whirlwind created in the laboratory. There are many different types under study. In this model, air is rotated by a moving screen that surrounds the chamber. Following a basic law of physics, the rotation concentrates in the center and is made visible by feeding smoke into it. The funnel changes size as the chamber is rotated faster. In nature, the updraft and rotation are often produced by a huge rotating thundercloud. The flow of air in all parts of the funnel has been closely studied, along with the effect that explosions have on the circulation. The energy of an actual tornado is so great, however, that it's doubtful that this method could ever be applied in nature. In another model, studies have been made on the funnels that are created when the angle at which air enters the chamber is controlled. By increasing the angle, the funnel becomes larger, and a pair of funnels appear. A further increase creates a family of smaller concentrated funnels, all rotating around a central core. There is evidence that the main funnel of some large tornadoes contains several concentrated areas like this, called suction spots, and that they cause most of the spectacular damage. This particular dust devil shows this same suction spot structure. A group of concentrated whirlwinds rotating around a common central point. In the path of actual tornadoes, it is sometimes possible to see spiral ground markings. These are thought to be made by suction spots as they trace out their path across the ground. The greatest damage would be in the path of a suction spot and could result in one house being destroyed and a nearby one remaining almost untouched. The role of lightning in tornado formation is studied here in a model produced by 5,000 volts of electricity. The funnel is a hot plasma of ionized gas, the heat from which makes the air rise. Great displays of lightning often occur with tornadoes, and at night unusual electrical effects have been reported. All this has led to speculation that lightning may indeed have some role in the tornado life cycle. But still, the problem with this and all models is relating what is produced in the laboratory to the weather conditions around a real tornado. Tornado studies are not limited to the laboratory or even to the Earth's atmosphere. Photography from satellites is now a powerful tool in tornado prediction. The satellite is launched into a circular orbit to an altitude of over 22,000 miles. There it revolves with the Earth, staying stationary above a particular point on the surface. The movement of cloud patterns during a single day can be viewed over and over for clues to tornado formation. These photographs discovered that a 300-mile-wide jet stream of air originating over the tropical Pacific Ocean helped to trigger a tornado outbreak in the Midwest. Sunset and nighttime darkness are moving in at the right as the Earth rotates beneath the satellite. The moving dots have been added to show the position of actual tornadoes that existed under the cloud. On May 11th, 1970, satellite photographs showed a line of huge thunderstorms developing over the western United States. This one, over Salina, Kansas, is nearly 100 miles wide. This somewhat smaller storm, developing over Lubbock, Texas, generated 2 tornadoes, taking 28 lives and causing a record toll in damage. Studies have shown that 27 of the 28 deaths occurred in the path of the suction spots rotating within the walls of the mile-wide funnel. These suction spots probably had winds 100 miles per hour higher than those in the rest of the main funnel. As tornado and thunderstorm research continues, the ability to warn a community that a tornado is about to strike is continuing to improve. For instance, the warnings at Lubbock and Topeka and many other cities were made possible by locating the tornado with radar. New radar techniques are able to locate a tornado circulation well before any funnel actually forms. The circulation which produces a tornado often shows up on the screen as a hook-shaped radar echo. Radar, time-lapse photography, water spouts, dust devils, satellites, laboratory models, all are indirect tools in the study of nature's most violent windstorm. The methods of study are limited only by the imagination of people and by the money provided to carry out their ideas. The complex puzzle of why and where the next tornado will strike is slowly being pieced together.